I am a performance nerd. I enjoy experimenting with code to determine how to make things run better. At my prior shop, there were vendor tools and SMF reports available to me to find and tune a hotspot. A hotspot is a piece of code that uses more CPU than the rest of the program. On the Xplore machine, those tools are not available to me. So I started searching for ways to capture the CPU usage. I found the time used macro. In order to measure the impact of various coding techniques, one needs to know how much CPU is consumed by the target code. This video explains how to get the CPU time in microseconds using an assembly routine. Welcome to another episode of Dinosaur Parkour, Faster, Better Mainframe Programming. I am Chris P. Fried. This is a small assembly routine. It is 79 lines long and most of the lines are comment lines. It slewed all of the asterisks that are coded in column 1. There are 43 lines of comment. Before doing a code review of this routine, let us take a look at how the routine is used. Flip the display so that its slewed lines are shown. The comment from line 6 to about 30 explain how to invoke CPU time. Notice the important note on line 6. CPU time must be invoked dynamically. Line 9 assigns the program name of CPU time to a variable, and on line 15, the call verb uses the call variable format. This ensures that CPU time is invoked dynamically. CPU time uses the time used macro. The manual states that time used returns an integer and a double word. Line 10 and 11 define the fields to be passed into CPU time. Those two fields must be defined as a double word that can hold an integer value. In assembler, there is a data type of double. The part about holding an integer value tells us that it is not a floating point value. In COBOL, that means defining the field as binary or comp5. I decided to use comp5, but the usage clause of binary or comp also works. Comp5 tells the compiler to treat this as a native binary field. Thus, the entire precision of the field is used, which is 19 digits. The precision of comp or binary is controlled by the picture clause, and the maximum is 18 digits of precision. Microseconds mean that the scale needs to be 6 digits. The start and end fields defined on line 10 and 11 have a range of 0 to over 18 quadrillion seconds and a scale of 6. Line 27 explains that the field defined as 912V96 are seconds and microseconds. To define the field as microseconds only, use the format shown on line 28. Line 14 to 25 explain how to use this routine to capture and display the CPU second used by a piece of code. There are 4 stages. The code to be measured is denoted as stage 2. Before executing the code of interest, we need to get the start time. This is done by calling CPU time to get the amount of CPU used by the program thus far. That is what line 15 does. The code to be measured, run. Notice that there is a loop here. Executing a piece of code once might not use enough CPU to be measured. The loop can be used to execute the target code enough time to measure it. When it's complete, call CPU time again to get the end time. This is stage 3 on line 21. In the 4th stage, the program calculates the difference between the end and start CPU time and displays the result. That is how to use this CPU time routine. Before moving on to the code review, consider this code. This test program is measuring something on line 38. I do not want to explain in this video what is being measured, but I will say that the target code involves two data structures which are named CB1 and CB2. Line 37 passes those two areas to A31BR14. That is an A mode 31 version of IEF BR14. So why did this code pass the two data areas to the do nothing program? It tricks the compiler into thinking that the data areas named CB1 and CB2 are being updated. Thus, the compiler cannot hardcode the logic in the paragraph named invoke test. Just be aware that the compiler can optimize your test code too much. You might have to trick the compiler into not doing certain optimizations so that the code you test is functionally the same as the production code. On to the code review. Line 2 names this routine CPU time. It uses 31-bit addressing per line 3. It can be loaded in 24 or 31-bit address space per line 4. Line 34 to 40 handle the program entry. The save area is part of the code section, which means that this program is not reentrant. I think this is fine because 1, this program is small. 2, it is more of a debugging routine rather than a production routine. And 3, I want this routine to be as fast as possible to minimize the CPU used by this routine since the end call during stage 3 gets included in the uses. Line 49 to 54 are the meat and potatoes of this routine. Line 50 loads the first parm into register 2. This parm should point to a binary double word. Time used stores the answer in this area. Line 51 invokes the time used macro. It asks for the current CPU time converted to microseconds to be stored into the address pointed to by register 2. If time used ends with a return code of 8, line 53 tries invoking it again. That is what the manual says to do. I really hope the manual is correct and this does not trigger an infinite loop. If the return code is higher than 8, line 54 jumps to the add-bin. If the code is less than 8, it drops into the done section, which restores the registers and returns to the calling program. It is a handy little routine if you already suspect a piece of code uses too much CPU and you want to tune it. I realized while editing this video I should explain what happens when CPU time is called the wrong way. Welcome to the final chapter, the wrong way. The member CPU bad is a program that demonstrates what happens when CPU time is invoked both dynamically and statically, calling it the correct way and the wrong way. This gives an overview of how CPU bad proves that a static call gets invalid numbers. Line 34 performs the paragraph that invokes CPU time dynamically. The call variable method is used as shown on line 53. This is the correct way to call CPU time. Line 37 performs the paragraph that invokes CPU time statically. Line 69 uses call literal. In order for Enterprise COBOL to treat that as a static call, the compiler option of no-dynam must be in effect. On line 1, no-dynam is being set using the CBL directive. This is the mainline portion of the procedure division. Line 30 through 32 performed a loop to burn some CPU cycle. Line 34 performed the dynamic call paragraph 3 times. This shows the dynamic paragraph. CPU time is invoked dynamically on line 53 to get the CPU used so far. This is our start of measurement time. Line 55 through 57 burns some CPU cycles by calling A31BR14 750,000 times. That is a do-nothing program. It contains one verb, go back. It does not do anything except return to the program that calls it. Line 59 does another dynamic call to CPU time. This is the end of measurement, CPU time. Line 61 performs the paragraph to calculate and show the amount of CPU used by the loops on line 55 to 57. Line 85 calculates the difference by subtracting start CPU time from end CPU time. That is the amount of CPU used by the loop. The values are displayed on line 87 through 89. The static paragraph is coded logically the same as the dynamic paragraph with one major change. The program name CPU time is invoked statically on lines 69 and 75. Notice that the paragraph on line 34 and 37 are performed 3 times each. Now that we know how the program works, it's time to run it by submitting the test JCL. The job is complete. Use the question mark to expand it. Select the sysout. This shows the results for the dynamic call. Remember, this was performed 3 times. The first iteration takes 21,423 microseconds to call the do-nothing program 750,000 times. The second iteration clocked in at 21,343 microseconds, and the third iteration used 21,449 microseconds. The other thing to notice is the start time for iteration 2 is very close to the end time for iteration 1. Same for the start time for iteration 3. The start time is very, very close to the end time from iteration 2. These timings are valid, and I'll offer an extra proof in a minute. But first, let us take a look at the numbers from the static call to the module named CPU time. These numbers are crazy. The value for the difference in the first static call is an overflow of the edited picture clause. The edited picture clause was coded for 18 digits of precision, and the end call got back 19 digits. Even looking at the second and third iteration, the difference is over 22 trillion seconds. That's more than 700 years. Crazy wrong. So which numbers are correct? The one from the dynamic call or the one from the static call? Consider this. Just prior to the go back, CPU time was invoked the final time. The CPU start time was set to 0. The code does a dynamic call to get the end time. Line 43 and 44 format the results. Select the JS system messages DD. The CPU reported for the bad CPU step is 0.19 seconds or 1900ths of a second. This matches up with the result from the last dynamic call. With just a bit over 193,000 microseconds. This shows that calling CPU time dynamically gets valid values. Why does the module CPU time get crazy results when a static call is used? Some folks might wonder if the issue is caused because CPU time is being invoked both dynamically and statically in the same run unit. No, that is not it. I've tested that also. It is a static call, and I have not been able to figure it out. If you have any ideas, please let me know what they are in the comments. Please subscribe, and thank you for watching.